This is another Higgs video. It's called Stabilized Neutrons, Higgs Boson Particle, Mass Nova, LHC. The research was done September 22nd, and I'm filming it on November 15th, 2012. My thoughts. Another keyword was stabilizing the neutron of a mass particle, Higgs boson. So I'm going to Google it, and up comes a quote. A Higgs particle is a highly unstable particle, visible only through its decay products. It has zero electric charge, and unlike all other known elementary particles, no intrinsic rotation or spin. These null properties reflect the fact that many Higgs particles, uniformly distributed through space, build up the Higgs condensate, which we sense as emptiness or pure vacuum. Although individual Higgs particles are highly unstable, a uniform distribution of them is stabilized through their mutual interactions. Visible Higgs particles are disturbances above that uniform background. As mentioned before, theory does not predict what mass a Higgs particle should have. Masses anywhere from 10 gigaelectron volts to 800 GeV might be accommodated, though problems start to emerge near either extreme. Physicists commonly use GeV as the unit of mass for elementary particles. 1 GeV is close to, but slightly more than, the mass of one proton. Because Higgs particles are unstable, to study them, one must produce them. That requires concentrating lots of energy into a very small space to create enormous energy density. The required concentration of energy is achieved at particle colliders. At the LHC, two counter-rotating beams of high-energy protons are made to pass through one another or cross at a few points. At each crossing, some fractions of the protons, which are moving in opposite directions at very close to the speed of light, collide. The collisions provide fireballs that explode into tens of hundreds of stable or near-stable particles, including electrons and positrons, pi mesons, photons, protons, and antiprotons, and several other possibilities. And this is from www.pbs.org. One process of Higgs particle production and decay is depicted in this sketch. So it says photon, and then it has the Higgs particle, and it's got top, anti-top, gluon, and proton. Okay? The sequence of events in the sketch above unfolds reading upwards. Gluons inside the fast-moving protons convert by quantum fluctuations into a virtual top quark and its antiparticle. The virtual top quark and antiquark swiftly recombine into a Higgs particle. Then the Higgs particle decays by a similar mechanism. Quantum fluctuations convert it into a particle-antiparticle pair, which recombine into two photons. At the end of the day, it is those two photons that are observed. I'm particularly fond of this exotically beautiful quantum process, which I discovered theoretically in 1977. Isn't that cool? The point is that more conventional processes, i.e. processes that don't involve Higgs particles, but which produce two energetic photons, are fairly rare. Thus, the calculated contribution from Higgs particles, should they exist, can be discerned above the background. The standard model is incomplete. Notably, its equations postulate 4 different forces: strong, weak, electromagnetic, and gravitational, and 6 different materials they act on. But to make the unified theory work quantitatively in detail, we need to expand the equations of the standard model so they integrate a concept called supersymmetry. Supersymmetry has many aspects and ramifications, but 2 are most relevant here. First, supersymmetry for experts, more specifically focus point supersymmetry, predicts that the Higgs particle mass should lie in the range of 120 to 130 GeV. Finding Higgs particles with mass in that range would give strong circumstantial evidence both for supersymmetry and for the unification that supersymmetry enables. Second, supersymmetry predicts the existence of many additional new fundamental particles, besides the Higgs particle, that should be accessible to the LHC. So if supersymmetry is right, the LHC will have many more years of brilliant discovery in front of it. And again, that's on the www.pbs.org website. That's where I found it. September 19th, my thoughts. How big does the Higgs particle need to be to study it? Quote, Higgs particle mass should lie in the range of 120 to 130 GeV. So I'm going to Google the mass particle 120, 130 GeV, and I'm going to explore this in the next video. Thank you for watching.